Am I audible? Biswajyoti, can you just confirm if I'm audible or not? Hello?
Hello, you're audible, audible.
Okay, okay. So let us start then. So in this lecture, we'll see the matrix norm and condition number because matrix turns out to be a very important entity while dealing problems in numerical analysis. And as it turns out, certain linear algebraic techniques that we learned in the last class. Who is this? Okay. Yeah. So certain linear algebraic techniques that we learned in the last class has way more application in this subject also than we can think of. So let us start.
Can I ask a question, sir?
Okay, sure.
Uh, Actually, last class, no, you have mentioned about one insightful question that when we are doing these row operations, simply
Yes,
by adding or subtracting with another row with certain factors, why the
yes,
equations are not changing. So
yes, exactly. So could you figure out?
I could not find out a convincing answer for that. Can you please elaborate that? Because
Sure, sure, sure.
yeah,
Okay. I'm glad that you asked this question. So we'll start with a simple 2 by 2 equation. Okay. Let us say if I give you
your
2x.
screen is not visible. Is it visible to all?
Oh, okay, okay. Thank you for reminding me. Yeah. Sometimes, yeah. Taking care of all other external factors, sometimes you forget the most important one, which is sharing the screen. Now is it visible?
Ah, yes, yes, yes.
Okay. So let us have 2x plus 2y equal to, let's say, 4 and x plus 3y equal to 4. Okay. Now, if you convert this into the metric system, can you tell me what will be the matrix form?
It will be a 2 by 2
Yes.
matrix.
So tell me the form. It should be
2, 2, 1, 3.
2, 2, 2, 1, 3, and on the right hand side you will have 4, 4. Correct? Yes.
Yes, yes.
Now, if I were to ask you what kind of row operations will you have the intention to perform, there is an obvious choice, right? How will you perform? Which row operation will you go to?
We can try to make that 1 to 0. That
Yes, you can try to make R2 this entry, right? This entry
yes, yes.
to be 0. For that, you need to perform R2 goes to R2 minus half R1, correct?
Yeah.
Yeah. And can you tell me the system? Yes. So because we're applying row operation on the first row, so the first row will remain unchanged, right? And quickly tell me the entries for the second row for this system.
That will be 0, 2,
Are you
and
sure? Yeah, 0, 2, and
2.
2, right? And what is the corresponding system? Can I write it as 2x plus 2y equal to 4, and it will be 2y equal to 2, right?
Correct. Correct.
Yes. Now you know the backward substitution. What will backward substitution give you?
Y equals to 1.
Yes. Now it will give you y equal to 1, and then
X equals to 1.
if yes, and 2x plus 2 times 1 equal to 4. Step by step we'll go, which implies 2x equal to 2, and so it implies x is equal to 1. So therefore, x equal to 1 and y equal to 1 is the solution. Now your question is, when we get this system, so here we have, let's say, this augmented form S1 and this augmented form S2, right? Why these two should have a same solution, correct? Am I correct?
But actually, if we plot these lines now, that they may not exhibit the same line, right?
Yeah, they may not exhibit the same line. That is true. That is true. For example, here the lines are, if you plot this, we are not saying the equation will be same. We are not saying the equation will be same. We are saying the final answer will be same. It
Okay,
happens,
okay.
I tell you why does it happen. So roughly speaking, when you convert one system to another, the system does not lose the solution that it has to have at the very first step, and it is precisely because whenever you are adding and subtracting, your final answer does not change. See, if you were to see through it directly, what did you do? You just added second equation to the you just subtracted first equation from the second, right? Some scalar multiple of first equation you subtracted from the second row. Now think logically, should it change the solution? How will you attain this row? You just see the second row. How will you attain this row? See, only the second row is changed, right?
Correct.
And who is? Yeah. So and how does this row come into the picture? You just what did you do? You took the second row itself and you subtracted some scalar multiple of it, and then you get the this equation. Now addition and subtraction does not change the solution. Addition and subtraction does not change the solution. I One more reason, if you are not mathematically, let us say this is our system ax equal to b. Okay, ax equal to b, and let's say we are getting some a1 x equal to b1, this solution, after first row change. Okay. So what is the relation between this a and a1? First thing, the relation between a and a1. Second, what is the relation between, this is a very good question, okay, b and b1. Now, okay, all of you agree if I start with ax equal to b, and if I multiply it with some metrics, let's say, you know, PAX should be PB. All of you agree?
That's correct. Yeah.
Yes. And if P is invertible, let's say P is invertible. P is invertible, then can I say this is if and only if? Can I say? Because if PAX is PB, then because P is invertible, so AX will imply B because P is invertible. Is it clear? Why this if and only if holds? Please say yes or no.
Yes, sir.
Okay. What about you? The person who asked this doubt? I'm
Yes, sir.
I'm
Yes, sir.
have some patience. I am going to answer your question.
Yes, sir. Correct.
Okay? Yeah. What is your A here? A here is 2, 1, 2, 3, and your A1 is
Sir, is it using Gauss elimination method?
no. In the last class, I asked why why does the solution remain same after applying so many row equations? Do you remember?
Okay, sir. Yes, sir.
So this was his doubt. I am clearing that.
Okay, thank you.
And what is A1? A1 is, what did you do after first row change? What do you get after first row change? This thing, right?
Correct.
So what is A1? A1 should be 2, 2, 0, 2. Let us also write B to be 4, 4, and here B1 will be, quickly tell me what will be the B1? 4, 2. Okay. Yeah. Now if I take my P to be, let's say, mm, just a minute, let me think. Is this invertible matrix? P is invertible, right? P is invertible or not?
Invertible.
Yes. Now tell me what will be AP or PA. 1, 0, minus half 1, and your A is 2, 1, 2, 3. So can you quickly tell me what will be the final answer? See, there is a very strong reason and intuition as to why we are doing this, but you need to have a little patience so as to see why we are doing this. This will just answer your question, believe me. But first, do the computation. What is P times A? Bishwajyoti?
Yes, yes, sir. The
Yeah.
first row will be 2, 2.
Okay. 2, 2.
Sir,
And
where from P came, sir? Could you please explain?
I
Capital
will
P.
explain. I will explain. I will just explain. I was coming to that, but but you need to answer me first, okay?
Yes, sir.
Yeah. What is the second row?
3 by 2, 3.
No.
Is it 0
Yes.
and 2?
Yes. 2. Is it A1? Is it A1?
Yes, sir.
Yes. And what about P times B? Can you do P times B? This will be 4 and this will be 2, right?
Yes, sir.
So is it B1?
Yes, sir.
Yes. Okay. So let us start from the beginning. So the question was why under row operations the solution does not change. So to see this, we started with this example. Okay. When we started with this example, 2x plus 2y equal to 4 and x plus 3y equal to 4. So the step one will be converting it into the converting it into the metric system. And the corresponding augmented matrix would be 2, 2, 4, 1, 3, 4. Then if you follow the naive Gaussian elimination method, then the row operation you would choose is the following: R2 goes to R2 minus half R1. Am I correct? And after
Yes,
that,
sir.
you get this second system, which is denoted by S2 here on the screen, this thing. So it turns out what we just saw. So this system is Ax plus B, and the second system is A1x equal to B1. So what did we do? We started with Ax equal to B. Then after one row operation, what was the row operation? R2 goes to R2 minus half R1. We get a new system A1x equal to B1. But it turns out that PA equal to A1 and PB equal to B1. So now does that answer your question? At least in this case, you can see the solution should not change. Because let x be the solution. Let x be such that Ax equal to B. And let y be such that A1y equal to B1. Correct? What do we want to show? We want to show actually these two solutions are same, which means we want to show x equal to y. And how do you show it? You see ax equal to b. So this will imply p ax equal to pb. And because p is invertible, so this means if and only if, because p is invertible, but we saw that pa is a1 x and pb is b. Now, oh sorry, this is b1, but b1 is what? B1 is your A1Y, correct? B1 is A1Y. So here you will have A1 x minus y equal to 0. And in this case, because A1 is invertible, you will have x equal to y. So the solution has to come same, okay? Because we are dealing with unique system here. If whenever there is a unique solution, it will be same. Okay? Do you get my point?
Sir, you told me to explain where from capital P the matrix 2 by 2 came.
Yes. But is this clear, first of all?
Yes, sir, it is clear.
Okay. So this is remark 1. Let us take this as remark 1. Vishwajyoti, is this clear to you?
It is clear, sir. What I was trying
Hmm?
to comprehend from that, if you graphically plot these two equations, no, that equations will be changing, but it will be passing to the same point. That is the
Yes,
essence of
yes,
this.
yes,
Okay.
yes.
Okay.
Now I will tell you where this, how, where did I write this P from? Okay. So you see, there was this row operation, right? R2 goes to R2 minus half R1. And before that you had some, so if 1 1 0 0, if you apply this row operation onto this matrix, what will you get? You'll get 1 0 minus half and 1. Am I correct?
Yes, sir.
And this was your P. See, please note that whenever you are performing a row operation in the system, it is equivalent to pre-multiplying the system with an invertible matrix. Do you get my point?
Yes, sir.
So here this matrix was P. So for example, you know, I'll just write it. Let's say x equal to b. You apply some row operation. Okay, let's say R. Something row operation. Okay, some row operation. Then you will get
And
a1x equal to b. One.
if we
But
apply
it
the
will be like
same row operation on I2,
yes,
then
yes, yes, yes. So you will get some p1 ax equal to p1b. This will precisely what you will get. This is your system. And where will this P1 come from? You apply the same row operation on the identity matrix. Again, you apply a row operation. Again, you apply some row operation, you will get A2x equal to B2. But it will be like applying another, pre-multiplying another matrix to the previous row operation. And so therefore, eventually you are multiplying a finite sequence of invertible operators to your given system. Am I correct?
yes, sir.
It's a good explanation, sir. Thank you.
Yes. So whatever solution you will get as in the final one, Let's say you stop at some a n x equal to b n. When a n is upper triangular, this is where we stop, right? So eventually you must have multiplied it by some, let's say pn minus 1 up to some n invertible matrix you must have multiplied. Am I correct? So eventually you are multiplying with, all of this product will be some invertible matrix. Let's say QAX is QB. So whatever solution you get here, let's say you get some Y which solves this system, which means QAY equal to QB. Now because Q is invertible, you will have AY equal to B. So this Y is also solving A. Okay? Is this clear? Y is also solving the original system. See, what is the aim? You start with the system and then you find some solution. You want to find some solution. Now we are taking help of the row operations and we are saying after finitely many row operations, whatever solution we are getting, if we are getting at the final stage, that will also solve the original system. Am I correct? Am I correct? This is what we are saying.
Uh, this AY is equal to B is eventually the same system.
Yes, because again I am saying whenever you are doing row operation, you are just multiplying this system by some invertible matrix. Let's say Q. So here if you are getting, some solution, let's say X tilde, then this X tilde also solves the original system.
Yes, sir. A inverse B.
AX equal to B. And why does this happen? Because Q is invertible, so you can cancel them. I should not use the term cancel them, but in mathematical, I'm just saying in some
Yes,
day-to-day life
Q.
lingo.
Q inverse
Okay?
exists. And,
Yeah.
hmm.
So you are not losing anything solution wise. Okay? You are not losing anything solution wise, and this is what we want. We want a solution.
So both
We
side,
all are.
we are getting the same multiplier, same matrix multiplier, Q.
Yes, exactly, exactly. That is why this method works. Okay?
Yes, sir.
So this was a nice question. I hope you find this explanation reasonable enough. So let me just put some remark. Yeah. If we begin with a system of linear equations, Ax equal to b, then after Gaussian, yeah, I won't use this term Gaussian, yeah. After finitely many row operation, a solution of new system, a solution of new system, a tilde x equal to b tilde, or we will use x tilde, a tilde x tilde equal to b tilde, also solves ax equal to b. That is a x tilde equal to b. Is this clear? This is what we just discussed, right? Please tell me if you have any doubt. Vishwa, Vishwa Jyoti, do you have any doubt?
It is clear, sir. Clear, sir.
Okay. And Biswajit, now do you know where this metrics come from? What we are pre-multiplying? This is
Sir,
not some arbitrary metrics.
as I understand
Yeah.
that if we apply the same row operation on an identity matrix after
Hmm.
pre-multiplication, what we are getting is called capital P.
Yes, exactly. And this is precisely what happens. Okay. Acha, okay, let me ask you a very basic question. Why do we only perform row operation? Why don't we perform column operation? Do you get my point?
Yes, sir. Um, um, do you mean to mix up row operation with column operations or only column operations?
Let us do first step by step, no? Mixing
Yes, sir.
column and row, we know first we need to okay, we have studied row operation. We know row operation is helpful in solving a linear system. Now my question is, why are not we considering the column operations? Or can we consider the column operations?
Sure. I think if we apply the column operations,
Mm.
the system will look like different.
The system also looks different here, no? When we apply row operation. System does not remain same. After any operation, system remains system does not remain same. But under raw operation, what is happening? The
Yes,
solution
sir.
is, the solution works. Will the same methodology work for column operation? That would be my question. কোনো তাড়াহুড়ো না করে আপনারা সময় নিন, ওকে? Take your time.
You are fluent in Bengali also.
Sorry.
You speak Bengali also.
Oh, Bengali you are saying, okay. আমি একটু জানি। খুব না, কিছু কিছু আমি জানি। So is the question clear to you? All other. So we have Rahul here, we have Anuj here. Rahul and Anuj, is the question clear? So the second question
Yes,
is,
sir.
see why we are discussing all these questions, because these are very basic questions. They don't need any kind of fancy methods, but these are just observations. Again, if a method is developed a certain way, we have to see why this is working, right? If, for example, if I wash my hair with detergent soap, we know that it is not such a good idea, correct? Intuitively, we know that detergent soap will not be a good fit for our hair, or a hand wash would not be a good fit for our clothes. So there are certain things that do work because they are designed to work such a way. Similarly, here also, the question is, what about the column operations? You have, again, I am writing these two equations. 2x plus 2y equal to 4, x plus 3y equal to, was this the equation? X plus 3y equal to 4, yeah. Okay, let us see what happens. Okay, 2, 1, 2, 3, 4, 4. Now, one preferable column operation could be C2 goes to C2 minus C1, right? Am I correct? Because then this thing will be 0. Am I correct?
Yes, sir.
Yeah, so what will you get then? So first column will be as it is. Then it will be 0, 2,
0, 2. Yes.
and you see now you write down the system. It will be 2x equal to 4, then x plus 2y equal to 4. You know here the solution is 2, and if you put it here, you will get y equal to 1. Am I correct? But this
Yes, sir.
system, this solution does not solve the original problem, does it? The solution is 1 1 for the original problem, but here we are getting 2 1. Everyone can see this?
Sir, it does not satisfy the original system.
Yes, exactly. Does not solve the original system.
That means system is not comparable or equivalent. We have
Yes,
got
yes,
a not equivalent system.
yes. We call this apple and oranges theory. You know why? You know apple and oranges, right? All of you eat apple and oranges. In English, there is a saying, we should not compare apple and oranges, right? You know, what does it mean? You should not compare two different kind of things. So here, when you are performing, column operation, what you are doing, you are adding y to x. Am I correct? When you are performing
Yeah.
column operations, you are adding y to x. You see? Am I correct?
Yes, sir.
Sir, adding y to
Uh,
x means
Adding y to x means what did happen in this thing? In this column operation, what did happen? You took C2 minus C1, which
yes,
means you took 2 here and you subtracted it with this 2. Am I correct?
yes,
So subtraction is also addition. Okay, so let's not be very sentimental about it. So we
yes,
just
sir.
added, this two, the minus of this two with this two. So what did we do here? We compared apple and oranges, right? We took something from oranges and we gave it to apple. This is not fair. Two different variables should not be mixed.
Hmm.
Logically, you think, before going to mathematical interpretation of anything is logical. You have to find values of x and y. X and y are independent things. And
That
when we
means
are doing column operation, yes,
we are performing operations. We are performing computations with the coefficients of x and coefficients of y and mixing. This is the
yes,
problem.
and this is the problem. Yes.
Yes, sir.
Why this is the problem? Because, see, even with single equation, it will change, right? This equation becomes 2x equal to 4. And this is not fair because the original equation was this. Whereas when you do row operation, what happens? You
Operations means
compare
we are doing operations on the same coefficient of same variable, either
exactly,
in x or
exactly,
in y.
either in X or in Y. So that is precisely why the row operation works. Okay, you are not mixing the variables.
Yes, sir.
So that is why it's not like we prefer to work with row operation. No, there is no such thing as preference. That is why the row operation works, whereas the column operations do not work. Okay, get this thing very straight. So next time when you're confused what to apply, row operation and column operation, now you have a certain aspect of knowledge as to why row operations will work and column operations will not. Okay. Yeah. So then let us discuss some question. I have some questions for you guys as promised last time. Okay. So shall we do questions now? Some questions at least, then we'll move to some topic. Is this fine?
Sir, will it be from this week 3 assignments?
I don't know the week 3 assignment.
Okay.
Yeah. Okay. Anyway, these are some questions, that. So week 3, you must have learned up to this thing now, right? Okay. You please solve this system using the Gaussian elimination method. So use naive Gaussian elimination and find Z. And take your time. Okay. Is the question clear to all of you?
Yes, sir.
Okay. Are you doing?
Yes, sir.
Okay. Take your time. Okay.
Sir, as per your question, Z becomes 5.
Okay. Z becomes 5. Okay. Let others do.
Mm, uh, should I calculate other variables also, or that's all right?
No, no. That is all right. I am saying let us wait for others. Okay.
Okay, okay, thank you. Thank you.
So basically, the first step should be this. Okay, Biswajyoti, because you have done. So how many row operations did you need?
Sir, I am not Biswajit, I am Biswajit.
Oh, sorry, sorry, sorry. I'm extremely sorry. Yeah. So how many row operations did you need?
Sir, here actually two row operations.
So can you find out that matrix P1 and P2 in each case?
Mm,
So
no, I have
you
not
must have.
calculated.
No, I'm asking you to do. You so
Okay.
first row operation you must have applied, right?
I have applied both the row operation simultaneously.
Yeah, simultaneously that is fine, but they are eventually two, right?
Eventually, there are two operations.
Yeah. So here you will get some P1, here you will get some P2. So can you find this P1 and P2?
Okay, sir. I'm trying.
Yes, yes, of course. You have to do nothing, just apply those row operations on the identity matrix. So can anyone tell me other than Biswajit, what should be the first row operation? R2 goes to,
2R1.
yes, no, R2 goes to R2 minus 2R1. And this will give you 2, 2, 1. This will give you 1. Then this will give you 0. This will give you minus 1 if I'm not wrong. Then this will give you 1 and 0. Yeah. So what is the second row operation? Can anyone tell?
So R3 minus half R1. R3 goes to R3 minus half R1.
Biswajit, I know you have done. Okay.
Okay,
I'm
sir.
asking the other two. Yeah.
Okay, sir.
Yeah. Yeah. Yeah, you're correct. It should be R3 goes to R3 minus 1 by 2 R1. Then you will get 2, 2, 1, 1, then 0, minus 1, 1, 0. And here you will get 1, sorry, 0. Then here also you will get 0. And this will be 1 minus half, so it will be half. And this you will have 5 by 2. Correct. Yes. So z equal to 5 from this you can see. So what will be your P1 here?
Sir, P1 is 100
Hmm.
Minus
minus
210
210
minus of 01
Sir, minus.
of
001
01
No, no. Tell me the second row.
minus
minus
210
210
Minus 2, 1, 0. Okay. And here your P2 will be
100
1, 0, 0,
010
0,
because
1,
only
0.
third row is changing minus half zero
Yes.
one.
Minus half, 0, 1. Okay. Now I am going to ask you to verify this. It might take some time, but we have all the time. Verification. Let us say this matrix is, let's say, what should be named this matrix?
A tilde.
Let us take, because this is system 1, let us call it S1. Okay.
Okay.
And this is system 3, so let us call it S3. So can anyone check that S1, then P1, then P2? It should be S3, right? From what we discussed. Can you verify this quickly? Please verify this. I request all of you to verify this. So were you able to verify this claim? So let us take P1 S1 first. I will do 2211 4332 1113. So tell me. So it will be 2211. Then you will take the third row and it will become 1113. And what about the second row? See, all these computations have already been done. You just need to verify this. So it might be possible that in this case, I might be needing your assistance for this. Are you guys there working on this?
Yes, sir.
Okay. Take your time. Huh?
Sir, should we multiply from right hand side?
तुम्ही हम आके बोलो আমি জানি না hello
Hello.
yeah you tell me why should I tell you
Okay.
all this is yeah I have written just two matrices. You please tell me what will be their product. Already two rows I have given you. For example, this will multiply like this. So here you will have 0.
Next, -1.
-1. Okay. Then
+1.
last one. Very good. Last 0.
Yes.
So these two matrices are same, right? This one and this one. These two are same. Now, again, you can verify very easily that when you multiply this matrix, you know, P2, P1, S1, so it is just P2 is 1, 0, 0, 0, 1, 0, minus half 0, 1. Oh, sorry. And P1, S1 we have computed above. So it will be 2, 0, 1, 2 minus 1, 1, 1, 1, 1, 1, 0, 3. Yeah, yeah. So quickly tell me. So it will be 2, 2, 2, 1 because first row as it is. Then this means second row as it is. So it will be 0, minus 1, 1, 0. And third row we will get this by this. So it will be 0, right? Again I will get 0. Here I will get half. And here I will get 5 by 2. See again this is S3, right? Is this S3? These two matrices are equal.
Yes, sir.
Yeah, so why have I tortured myself to do all this drama? So as to make sure that you realize that whenever you are performing two raw operations, or for that matter, any finite chain of raw operations, it is just multiplying the previous system by an invertible matrix. Okay? Now you can see it very easily, right? Whenever you are applying one row operation to a given system of linear equation, of course, you will get another linear system, but the first linear system and the second linear system has a deep relation, which is the following that the new linear system is actually obtained by pre-multiplying an invertible matrix with the previous linear system. Am I correct?
Sir, you please repeat it once.
Yes, okay. So you have a, let's say, given system S1 here. Okay. This is S1. Let us say this system to be S2. How will you reach from S2? How will you reach to S2 from S1? Via performing some row operation. Am I correct?
Yes, sir.
But this is equivalent to saying that you obtain this S2 by multiplying pre-multiplying P1 with S1, right?
Yes, sir. P1 H1.
Yes. So whenever you are performing a row operation, it means you are pre-multiplying an invertible matrix. This is all what I want to say.
Sir, that means the second system is coming from two different ways, as I think. First of all, after some row operations, say R2 minus 2, R1, something like that.
Mm-hmm.
And S2 is also coming after pre-multiplying some invertible matrix P1, P1 and H1, product of P1 and H1.
Mm-hmm. Yes.
So if
Yes.
S2 is coming from two different ways, but S2 is same. Basically, S2 is same matrix.
Yes. 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 And when you are saying two different ways, that is not entirely true. When we are saying row operation, it is just some algebraic equation. But what I'm trying to tell you, corresponding to this row operation, you have an invertible matrix. Okay. So row operation is not arbitrary thing. You are actually pre-multiplying an invertible matrix. So
That
eventually we
means
are playing with matrix.
basically we are doing same thing.
Exactly. Exactly my point. Okay. So you can always associate a row operation with an invertible matrix, with a pre-multiplication with an invertible matrix. That is all. And
That
and
means
hence,
corresponding to.
Mm-hmm.
corresponding to every row operation, there exists an invertible matrix such
Yes.
that after pre-multiplication with that matrix, we will get the same system.
The new system. Yes. Yes. This
So
is
here
this is
this
exactly what.
this multiplication of this P1, P2 up to Pn, no, that will result in a identity matrix, right?
No, no, that is not the case. How will you see? When did you stop? When did you stop here? If you convert it into identity, no, then the original system, if this is identity, then S1 is S3, right?
Yeah.
No, that is not the case. That is not true. Because then ultimately we are starting with one system, we are doing some fancy things in between, and we are getting the same system. Then what is the benefit of doing all these computations in between if you're getting the original system? Always remember the original system is hard to work with. To make it easy, we are performing a row operation. Okay?
Okay.
Okay, tell me where is the confusion? I know there is some confusion. Please tell me. You be please as open as possible. This is a tutorial session. It is supposed to be full of doubts, and that is why we are sitting here. Okay?
Now, as initially Vishwajit has asked, no, that we are multiplying P1 S1, then that is multiplying with P2. If we do the
Yes.
multiplication P2 with P1, then with S1, then this P2
Hmm.
and P1 becomes an identity matrix.
If it becomes an identity matrix, it need not be the case, right? We are seeing here in this particular example, P2 P1 cannot be identity because if P2 times P1 is identity, then S1 is same as S3, which is not the case.
Okay.
Yeah. Okay. So let me ask you. So uh, have you studied modified Gaussian elimination method? Did you see the videos of those lectures?
So that is actually week 2 that is completed. Now week 3, the norms of matrix that is coming.
But Gaussian elimination you must have studied in week 2, right?
Yes, yes, yes.
Yeah.
Gaussian and the modified Gaussian, then all LU
So
factorization
modified
is over.
Gaussian is all I want to ask. Okay, let me then just put some modified Gaussian question.
Said modified means, do you mean some pivoting after some pivoting?
No, you tell me. You are taking the classes, right? You are
Sir,
seeing those video lectures?
as I can understand, you are you want to mean after some
No,
pivoting
no,
the system.
I I'm not talking about myself. Modified Gaussian is a very standard method that must have been covered in your classes. Are you seeing those NPTEL lectures? Just tell me very honestly, because otherwise we can discuss it here.
Sir,
If
sir, I might have gone through, but problem is that there is a huge amount of video contents and huge amount of assignments in every week we are getting. So every time we are getting confused, and it is not always possible to cover all these things thoroughly.
okay, so then it's better I discuss with you guys modified Gaussian elimination. Is that fine? It is just
Okay,
one
no
step
problem, sir.
generalization of Gaussian elimination. Okay. So do you remember in the last week we discussed some drawbacks of naive Gaussian elimination method, right?
Sir, drawbacks means when the A11 or
Yes, it's
A22
zero.
becomes very less or zero.
Zero. Yes, yes.
Yes, sir. Yes, sir.
So
Yes,
to
sir.
overcome that problem, we have Modified Gaussian elimination. If something does not work, then what will you do? You will modify it, right?
Yes, sir.
And this is what happens with this method also. This is, you remember in naive Gaussian elimination method, row exchange is not allowed, correct?
Row exchange.
Is not allowed. You cannot interchange two rows in the first Gaussian elimination method. For example, if I give you this method, 2x plus 2y equal to 0, or 2x plus 2y equal to, or maybe y plus 2z equal to 3, x plus 3y minus z equal to 3, or 2x plus y plus z equal to 4. And if I were to ask you apply the naive Gaussian elimination method, then you will say the method fails, right? Am I correct?
Yes, sir.
Yes, sir.
Because
Okay, let
A11
me.
is absent.
A11 is absent. Okay, just a minute. Let me write it. Mm. So this method fails. Reason because A11 is non-zero. But does that actually mean that we cannot solve the system?
Sir, A11 is 0.
Ah, sorry. A11 is 0. But should that mean that, we cannot solve the system? Question is,
Yes, sir. We can solve the system after some little bit modification.
yes, does this mean the system cannot be solved?
So we can rearrange the row in such a way that A11 will be the maximum out of all the rows.
Yes, yes. So this is precisely the modified question. You see, A11 is absent here. Okay. So what you
Yes,
do,
sir.
you interchange it with some row where A11 is non-zero. But which row to choose?
Non-zero and as well as maximum.
Yes, I am coming to that. Step by
Yes,
step,
sir.
let us go.
Yes, sir.
So you just choose one row where this A11 is non-zero. But there
Mhm.
can be many rows where A11 is non-zero. Am
Non-zero.
I correct?
Yes, sir.
And because we are defining an algorithm for computer, we are not defining it for ourselves. We want this method to work via some computer. So we need to define a step-by-step algorithm. Am I correct? Because
Okay, sir.
computer cannot judge which row to choose. That this axiom of choice thing does not exist for computer. So I have to specify, if there are more than one rows where this A11 entry is non-zero, which row to choose.
Yes, sir.
One good choice, one good way out for this, as you all suggested, is to just choose the largest A11 in terms of modulus.
Yes, sir.
Correct? So here you see you have two two A11s, which are non-zero. But which row to choose? And the
Third
idea
row.
is to you choose, yes, you choose the row where the modulus is greatest, which means the 2 is greater than 1, right? So you just interchange these two rows and keep everything as it is. Okay? So this is R2 goes to R1. Am I correct? This double sign means interchange. This sign means interchange. And y plus z equal to 4, it is 3. And the second row will be as it is. Okay. Now can you apply the first step of Gaussian elimination?
Yes, sir.
Can you do that for me? Convert it into an augmented system and tell me. So here you see the system will be 2, 1, 1, 1,
4,
3, minus 1, then 0, 1, 1,
4, 3,
4,
3.
3, 3. Now you tell me what row operation should you apply?
Sir, R2 goes R2 minus half R1.
Yes. Do I need to do anything for R3?
Not required.
Not required. Yes. Okay. So what it should be 2, 1, 1. It will be 0. 3 minus half will be 5 by 2. Minus half will be 1. Oh, sorry, minus 1. 4, then 3 minus 2. This will be 1. Am I correct?
Yes, sir.
Yeah. Now what will you do? So just write down the system. What is the system here? 2x plus y plus z equal to 4. See, I am not doing anything directly because I want you to understand what we are going through. Otherwise, I could have very well written the systems in the matrix form directly and solve it.
So this
So this is
last
5
row,
by
it is
2.
last row, is it correct? It is y plus 2z equals to 3, no? That equation was.
Where? Oh, okay. Yeah, thank you. Y plus 2z. Okay.
And that row
So here I
operation
should
also,
have
it
to.
should be R3 and R1 is interchange, not R2 and R1, right?
Yeah, yeah. Thank you. Thank you so much. Yes. Okay. Now is this correct? Yeah. 5 by 2 minus z equal to 1. Then y plus 2z equal to 3. Now what you do? You apply the same procedure here. What is the maximum? 5 by 2 or 1?
5 by 2.
So then interchange. Okay. So what will you get after interchange? This is R2 interchange with R3.
Here, why
2,
interchange is
1.
required?
Sir, why we are going to interchange? What is required?
Because this is we are learning Gaussian modified method. Okay, modified Gaussian elimination
Huh.
method.
Sir, but 5 by 2 is greater than 1. Means 5 by 2 is more. Coefficient is larger. So
Oh,
why?
okay. So we don't, yeah. We don't need this. Yeah, yeah, sorry.
Yes, sir.
This is already larger. Okay. Yeah, I'm so sorry. So here we do not need interchange. Okay. Okay. So then we continue with this system, what is given above, right? Now, which row operation
Yes,
will
sir.
you apply? I think R3 goes to
R3 goes
R3
to
minus 2 by 5 R2.
R2.
Yes, this is correct.
Yes, sir.
Mm. Then here you will have 0. Here we will have 12 by 5, I guess. Let us do 2 plus 2 by 5. Yes, 12 by 5 and 3 minus 2 by 5. So here we'll also have 12 by 5. Now we stop. As soon as we get upper triangular matrix, we stop. Okay. So what is your Z here? We apply in the last as we do for
1.
naive Gaussian elimination. So Z is 1. What about Y? Y is 5 by 2 plus, sorry, minus Z equal to 1. What does it imply?
5 by 2 y is equal to 2.
Just a minute. I think we have done some mistake somewhere. So here it should be 3 by 2, yes. Because minus 1 minus half, so it should be minus 3 by 2. Yeah. So if you follow this, then you will get y equal to 1. Am I correct? And finally, you have 2x plus y plus z equal to 4. You put y equal to 1, z equal to 1, you will get x equal to 1. So therefore, 1, comma 1, comma 1 is the solution. All of you agree?
Yes, sir.
Okay. Now I am giving you one question. You please tell me the answer. You have to use modified Gaussian, okay? Do not use naive Gaussian method. Yes, please.
फाइट करवा हमें तो ज्यादा करेगा लेकिन आज ही दो तारीख बार में फट गई आप बोलो बात तो लगे ले रहे कि बोल
Rahul,
रहे
please mute your mic.
तुम देख के लाते अच्छे से मैं तो देख के लाते हूँ हमेशा हाथ
Yes. Can you see the question?
Yes, sir.
Okay, please try to do it. So, anyone?
Sir, doing 1 minute.
Ah, take your time. Take your time.
Sir, is it 13 by 11?
No, I don't know. Okay, let us do. So first you must have interchanged the rows. So you will get this system. 4, 1, 1, 3. Then 1, 3, 3, 2. Then 2, 2, 1, 1. Am I correct?
Yes, sir.
Yes. Now, what draw operation did you perform? Okay, let me just do it this way. R2 goes to R2 minus 1 by 4 R1 and R3 goes to R3 minus half R1. Am I correct?
Yes, sir.
So it will be 4, 1, 1, 3. Then it will be 0. 3 minus 1 by 4, 11 by 4. 11 by 4. Then 2 minus 3 by 4. Then 5 by 4. Right?
Yes, sir.
It will be 0, 0, minus 1. Oh, sorry. No, not minus 1. Half. This will be minus half. Correct? Yeah. Have I done something wrong?
Mm, sir, last row I have obtained something different.
But this was your row operation, right?
Yes, sir.
So check. So 2 goes to 2 minus half times 4. It is 0. Then 2 goes to 2 minus. Oh, this is not true. Sorry. Yeah. 2 goes to minus half. It should be 3 by 2, right?
3 by 2. Yes, sir.
Now is it correct?
Now this is correct.
Okay. Now which one is bigger? 3 by 2 or this?
11 by 4 is greater.
Greater, right? So no need to interchange.
Yes, sir.
And how will you do the row operation? R3 goes to R3 minus,
6 by 11. R2
which
into
means
6 by 11.
just a minute. 3 by 2 minus, you have 11 by 4 here, so you need to multiply this and 3 by 2. Yeah, so 6 by 11.
Yes, sir.
So because you see, we are to obtain the value in Z. So I'm just computing the last row, okay? You'll have 0 here, then you'll have 0 here, then you have half minus 6 by 11 times 11 by 4, half minus 3 by 2. So you'll have minus half here. Oh, sorry, minus 1. Am I correct?
Um, yes, sir.
Yeah, okay. And what about the other side? Minus half,
Minus 15 by
minus 6
22.
by 11, minus 15 by 22. So it will be minus 11 by 22. So it will be minus 36, sorry, minus 26 by 22, which is minus 18 by 11. Am I correct? Oh, sorry, 13 by 11.
13 by 11. So Z equal to 13 by 11.
Yes. So this implies Z is equal to 13 by 11. Because we did only those computations which we need for the solution. Okay. Yeah. So is this method clear?
Yes, sir.
What do you think should be the drawback of this method? Or is there any?
Drawback of this modified Gauss elimination method.
Yes, just think for a while. Yeah, please tell me. At
Sir,
least there is one
if
sim. Yeah.
the largest element is more than one,
Mm-hmm.
then there may be a doubt which rows should come. Sir, I mean to say is that
If the
if the
modulus is
largest,
same, right?
yes, sir.
Yeah, yeah. That could be one. Because the classification criteria to choose the row is to select whose modulus entries is among all the modulus entries of A11, which one is the largest, right? So
Hmm.
this method will be confusing for the system if the modulus is same for more than two rows. Am I
Yes,
correct?
sir. Yes, sir.
Yeah, very good. Exactly. And what about the operation count? When
Operation
I say
number of operation.
yes, number of operations. For example, if I give you this system, x plus y equal to 1, sorry, x plus y equal to 2, and let's say 2x plus 2y equal to 4. You can apply naive Gaussian method here, right? Directly. And you can also apply modified Gaussian method also. That is true?
Yes, sir.
Okay. Let us just put it into remark. If I give you x plus 2y or x plus y equal to 2, then 2x plus 2y and 2x plus 2y equal to 4. Here you have naive Gaussian elimination, and here you can apply both of them. You can apply. So if you follow the naive Gaussian method, then it will give you 1, 1, 2, 2, 2, 4. And directly you can say R2 goes to R2 minus 2R1, right? And you will have 1, 1, 2, then 0, or just a minute, let me change this. Otherwise, yeah, sorry. Mm, 1, 3. So you'll have minus 1 and minus 1, right? Is this clear? And if you
Yes, sir.
follow the backward substitution,
We have y is equal to 1.
and then x is equal to 1.
1.
Now, but you apply modified Gaussian. So again, you will get this same thing. Yeah, but you cannot apply modified Gaussian directly here, right?
We have to interchange.
You have to interchange. So, so it will become 2, 1, 3, 1,
1,
1, 2.
1, 2.
Now you can apply the
Row
R2
operation.
goes to, yes, R2 goes to R2 minus half R1. And you will have
Yes.
2, 1,
1, 3,
then
and
0,
0.
minus half, minus half.
Hmm.
Or is it 1? It should be half here. Yeah. And then you apply backward substitution. You will get y equal to 1, and then x is equal to 1. Correct?
We are getting the same solution.
Obviously, no, you will get the same
Hmm.
solution.
Hmm.
But what I'm trying to say, you see which method is more complicated here.
Obviously, second method.
Yes, because the operation counts are getting bigger, right?
Yes, sir.
So if you're working on a system and you provide the system this problem, the system will take more time for modified Gaussian, right?
More expensive.
More expensive. Yes, that is precisely the term. That this method is more expensive. So even modified Gaussian has some, though we're modifying the method, but it turns out to be that it could be expensive for some particular linear problem. Okay? Do you get my point?
Yes, sir.
Yeah. So this can be thought of as a drawback of modified Gaussian method. Okay. Yeah. Now let us go back to the LU factorization. You know LU factorization?
Yes, sir. Sir, today I sent you a mail. I don't know whether you have received or not. Is it is regarding
Mm-hmm.
last day you asked me the topics you want to discuss, something like
But I
that.
did not
You
receive any mail.
but that may sir reach too late. Actually, I sent it late.
Oh, yeah. This is the mail.
Yes, sir, sir.
Okay, Cholesky method you want to discuss?
No, thoroughly, sir. Actually, other two methods are easier, but this method is not
Yes.
easy.
Okay, maybe. Okay. Mm, now I'm just thinking whether to start it now because it's already almost time.
Sir, another thing I want to just point out.
Mm-hmm.
Can you please
Mm-hmm.
repeat in very concise form the point you have started to discuss today?
Mm-hmm.
Means we have a system after applying so many row operations. The final system is equivalent to the initial system.
Yes.
Um, could you please explain in very concise manner again?
Yeah, yeah, sure, 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 sure. Okay. Okay, so let us, Chalaski, I will send you some link through this mail. If you still have, okay, you already, maybe, you work on a problem by Chalaski yourself and you send me exactly where you're having problem. Is that fine?
Sir, problem is uh, in what way or what are the easiest way to decompose the matrix in two matrices? I mean factorization, L and LT. The process. The problem is in process and how many operations it is taking. The count the number of operations. There are two problems.
Okay, then it's a lot of problem for us to discuss in within next 10 minutes. Uh,
Yes, sir. You
you
can
could
send some
have,
link also. No problem.
sure, sure. Okay, okay. Then I will do that.
Okay.
But okay, let us briefly discuss in the last minute what we started with. So these two methods are,
In order to share convince someone else, these two things
mm,
are identical. Even
mhm,
after imposing some row operations, the basic systems remains same. How
mhm.
one we can
No, do not
un-
say basic system remains same. You say at the final stage, whatever solution we get, the same solution will work for the original problem. Okay? Okay, let me just put it. Okay, you have a linear system, right? You start with a linear system. Am I correct?
yes, sir, AX is equal to B.
Ax equal to b. This is your. You start with this. Maybe I should also write. Yeah, so this is my system Ax equal to b.
Yes, sir.
What is our aim?
Our aim is to impose row operations
No.
in order to solve it.
What is our aim? Aim is to find x that satisfies Ax equal to b. That is our aim.
Yes, sir.
Or maybe let us put it more precisely. To find some x. There can be more than one, right?
Yes, sir.
That satisfies Ax equal to b. As you know, here x is unknown. So what do we do to do this?
Use Gauss elimination method
No, no, forget about Gauss elimination for the time being. We apply some row operation.
in order to simplify A.
Yes, some row operation to simplify the system Ax equal to b. Right.
Yes, sir.
When I say simplify the system means it means the system will have more zeros. Correct?
Yes, sir. Yes, sir.
Yeah. And we denote and we get a new system.
Hmm.
We get a new system A tilde some unknown x tilde b tilde. Okay, or maybe I could put it a tilde y
Why?
b.
Yes, sir.
Yeah. Here y is unknown. Okay.
Yes. Yes.
So when we are changing the system, so okay, this is enough to understand because here the linear equations has changed. Okay, the linear
The
equations.
system has changed. Yes, sir. System has changed.
Yes, yes, the linear equations are changed. So the question is, so a natural question is,
Can we have the same solution?
or rather, a natural question is, if some y that satisfies a tilde y equal to b, right? Because a tilde second system is easier to work with, so we will solve this system and we will get one y. Okay.
Yes, sir.
So natural question will be if this y that satisfies a tilde y equal to b also works for ax equal to b, correct? Because that is ay equal to b. Is the question clear?
Yes.
Yeah.
That means same Y should satisfy both the system.
Yes, yes, yes. Let us write it. This is a good line. That is the same y satisfies both the systems. इसका answer, the answer to this question is, as we have seen, is yes, right? The answer is
Hmm.
yes. Why? Because let a tilde y equal to b. Okay. Now, when you started with, or maybe let us put it like this, then we know there exists some invertible p because of row operation such that such that the new matrix A tilde was nothing but P times old matrix, correct? And the new vector B tilde is nothing but P times old vector. Am I correct?
Yes, sir.
Now, now you see A tilde Y is B tilde. Full stop this. This will imply PAY equal to PB. Am I correct? This will imply P inverse PAY equal to B, which is same as AY equal to B.
And it proves the required condition.
Yes. And we are done, basically.
Yes, sir.
Now, is this brief a good brief for you?
Yes, sir. Sir, one question is the recorded version. Will you will send the recorded version to us? Is it in the same format or there might be some changes?
Sometimes there can be some changes, but I try to stick to whatever we have written here. Okay. For
Okay,
example,
okay,
for today, I will post it. Okay.
okay. So, in the last format of what you have presented, i- will it be maintained in the same format? as you have
Yes. 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 Yes.
same. Yes, sir.
Yes. Sometimes what happens, whenever some question is left and we were discussing it, so I will complete the solution, then I will post it. Okay?
Okay.
Because
So
notes
after
should be complete. Yeah. Okay.
yes, yes, sir. Yes, sir.
Yeah. Yes.
Sir,
So,
another question.
yes. Mm-hmm.
Possibly you are using some software to present your materials you are writing, and we are able to see this.
Yes.
Can I ask, what is the app you are using, or what is the software you are using to discuss this?
See, I have an iPad. Okay. So, and that iPad is actually a writing one. You can write your, whatever notepad you are being shown, I'm able to write it on that screen and it is being shown to you. Or
Uh,
otherwise, for the simpler system, you can buy a notepad and connect it to your computer or PC or laptop and you will be able
yes,
to write. And to share what you do, you open your Google Meet, okay, like this. I'm showing you, okay. Then you
yes, sir.
go here. Can you see the share screen option?
Yes, sir.
Yeah, share screen. First is add others, second is in call messages, then is share screen. So you can share your screen. It
I will
will ask
share.
something. Huh?
You are asking me to share, or you are just showing me?
No, no, I am just showing you. Okay.
Okay,
Then you
okay.
can see my entire screen. Then I will open this app. In my iPad, there is an app called Notepad. You need something to write on. Okay. So this app is Notepad where I write. Now you can write.
Sir,
And
Notepad is a common app. It also belongs to some desktop also, and every desktop there is a Notepad.
for every desktop you can find. Okay. Don't worry. If you have some already, if you've already got some notepad, external notepad, you tell me, I will tell you the app. Okay, don't worry.
Okay, okay. So
Yeah.
you are writing using some pen, like
Yes, 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 yes. I show you, maybe that is a good idea. Mm, let me go visible. So this is the pen. Can you see some pen
yes,
in
sir.
my hand?
White color.
Yes, yes. So this is the pen. Yeah,
Yes, sir.
yeah.
And you are
So
connecting your device, external device, to either laptop or desktop, something like that.
no, no, I have an iPad now. So in iPad everything is there already. Okay.
Oh, okay, okay, okay.
Yeah. Yes.
Everything
So
means
just a
you are
minute.
connecting. You are connecting this link also through iPad, and you are
Yes,
opening the
yes,
mail.
yes. Because you see iPad, this have this Google Meet link. Can you see in the bottom menu? So I have Gmail where this 40 is written, right? Then I have calendar, then this green icon is there. This is Google Meet. Okay.
40 is written, then
So this
yes,
this
sir.
icon,
This calendar, then Google Meet.
this
Yes, sir.
icon.
Yes, sir.
Yeah, this icon.
Green.
Can you see this icon? Yeah,
Yes,
green
sir.
icon.
Green
Yes.
color. Yes, sir. Yes, sir.
Yes. You open it, you type the link here,
Mm-hmm.
and you join. And you
Mm-hmm.
share screen as I told you. Okay.
Mm-hmm.
Yeah.
So everything you are doing using just iPad only.
Yes. Yes.
Nothing more is required.
No. For recording purpose, I need some laptop. Can you see this account, Deep? One is there already. So Deep is this
Yes, sir.
laptop
Yes.
account that I use for recording the session. Okay. Because
Okay. Okay.
recording cannot be done in iPad. I mean, screen can be recorded, but my audio won't be recorded. Okay.
Okay. Okay.
Yeah.
So
But if you
using
are
some.
not to record the session, for example, if you want to teach someone
Mhm.
and that session need not require a recording, okay,
Okay.
then iPad is enough.
Okay. Okay. Okay.
See, why I have to record, right? Because these are the instructions. I have to record the session and put it on my YouTube channel, whose link I share with the NPTEL fellow, and they share it with you. That's how the process is.
Yes, sir.
Yeah.
Sir, can your iPad be replaced by some smartphone also?
See, smartphone you can do, but you won't be able to write it, na?
There may be
You won't be
some
able
app,
to write. Yeah, but it's very,
but
very small, very, very small. How will you write?
oh, iPad size is larger.
My iPad says like it's like a small laptop. The size is large.
Size is like laptop.
Yes.
Yes, yes, sir. Okay.
Yeah. Yeah.
Sir, if it is possible, you please you can send me the some suitable link of Cholesky method if possible, so that I can
Okay,
easily
okay.
understand how
Sure, sure,
can
sure, sure.
easily any kind of matrix or some suitable matrix can be factorized, can be decomposed into two factors.
Okay, just send me a reminder mail, okay?
Okay, sir. Thank you.
Because see, I will forget eventually because I have some other
Uh,
duties as well.
but sir, you have to open the Gmail account. Otherwise, how
See,
can I remember you?
okay, I will send you. But most of the time, what happens is because we are so busy. Uh,
Sir, maximum another mail I can send you.
that's what I was asking for. But okay, I will make sure I send you. Okay,
But
don't worry.
I do not have any other than your Gmail ID. I do not have anything for communicate to you.
No, that is fine. That is fine. I will send
Mhm.
you. Okay, don't worry.
Okay,
Okay.
okay, okay. Thank you.
Okay, then, if you have no doubt, maybe we can stop
Leave
this
today.
meeting.
Okay,
Yes.
sir. Thank you.
Yes. Okay, Biswa. Deep, hello? Deep, do you have some doubt?